Welcome to Spring LIB.
So a 65 centimeter guitar string, 6.5, 65 centimeter. It's fixed at both ends and in the frequency range between 1 and 2 kilohertz. We find the resonance to be 1.2, 1.4, and 1.8. And we want to know what's the speed of the traveling wave. So just by looking at this, because we have we see that all of these frequencies differ by 300 hertz. So if this is Fn, this is Fn plus 1, this is Fn plus 2, we can see that because the resonant frequencies differ by 300 hertz to each other, we can tell that the fundamental frequency F1 equals 300 hertz. So knowing that, we can find velocity v equals lambda times f. And of course, the reason we want to find the fundamental frequency is because we want to find the wavelength that is associated with the frequency. So we don't really have to use the F1, we can use F2. In that case, we will have this wavelength. In F3, we can have this wavelength, but usually we go to the fundamental frequency because we find it a lot easier to use this. The wavelength equals 2L. So it's 2LF, which is 2 times 0.65 meter times 300 hertz. This is 390 meter per second. And again, this is using the properties of the fundamental wave. If you do not like using the property of that, another way to do that is you can use one of these. For example, after we see that the fundamental frequency is 300 hertz, we can tell that 1.2 kilohertz is the fourth harmonics, 1.5 is the fifth harmonic, and 1.8 is the sixth harmonics. So for example, for the fourth harmonics, we will have a form like this. In this case, lambda equals half of L, and F equals 1.2 kilohertz. So in this case, we can also see V equals half of L times 120 hertz. But of course, you can see that it will be the same answer. It will be 390 meter per second.